Hello and welcome. In this video, I want to solve the one-dimensional Schrödinger equation for a very simple potential. It's the so-called particle in a box, also known as the infinite potential well. As we saw in workshop 6, this model system is an approximation to conjugated pi bond systems such as beta-carotene, long-chain molecules, nano-engineered structures, and does give some insight into the energy scales of atomic, molecular, and nuclear systems. So let's just write down the time-independent Schrödinger equation. So we have the rest mass of the particle here. It's in one dimension, so we have the ordinary derivative, d, not the partial derivative, and here's the wave function, or the eigenfunction, and you can see it's a function of x, plus the potential energy, and this is equal to the total energy. Now, I just want to reiterate that we can write this here in a slightly different form. If I write this as minus h bar squared on 2m, the second derivative, plus u of x, let this act on psi of x, I get e psi of x. And this object here, which consists of the potential energy and indeed the kinetic energy, is known as the Hamiltonian, or the Hamiltonian operator. And so what we can see is the Hamiltonian operator acting on the wave function gives us the wave function back, and it's multiplied by a real number, which in this case is the energy, or to be precise, the energy eigenvalue. So this is known as an eigenvalue equation. And the matrix formulation of quantum mechanics, which you'll meet in later years, the Hamiltonian is represented by a matrix. The eigenvalues of that matrix are indeed the energy eigenvalues of the system. So let's apply this to a simple one-dimensional potential. One-dimensional box, also known as an infinite potential. I have to be a little careful. Physicists refer to it as the potential, but strictly it's the potential energy. And the potential energy for the particle in the box is written like this. U of x is equal to, it's equal to a constant inside the box. And because the simplest constant is 0, I'll choose to set it equal to 0 inside the box. I'll explain why that's reasonable in a minute. And so this is for inside the box. And it's equal to infinity on the walls of the box and outside. All right, so let's sketch what this potential energy function will look like. So the potential energy function, here's the x coordinate here. I'm going to represent the potential energy function, also referred to simply as the potential, but remember it's a potential energy. And this is x equals 0, and I'm going to consider a box of width L. So this, for example, might be the distance between the carbon atoms in a pi-bonded ethylene molecule. Now, inside the box, we're going to set the potential equal to a constant. In fact, we'll set it equal to 0. Outside the box, or on the walls of the box, the potential energy will be considered to be infinite. And so there'll be 0 probability of finding the particle outside the box. Because the wave function is continuous, if there's 0 probability of finding it here, as I move closer to x equals 0, then continuity requires that actually on the walls of the box, the probability of finding the particle at x equals 0 must be 0. And likewise here, if there's 0 probability of finding the particle beyond x equals L, continuity of the wave function must be continuous, means that at x equals L, the probability of finding the particle on the wall is 0. Now, I choose the constant to be 0 because all I can ever measure will be energy differences. So if I were to put this equal to a constant which is not equal to 0, when I measure energy differences, that constant just disappears from the energy difference. So by putting it equal to 0, it doesn't change the physics. for this particular problem and makes the mathematics a little easier. So if I put the potential energy equal to 0, I need to solve for this inside the box. So the equation I need to solve for is this here. It's the one-dimensional Schrödinger equation for a particle in a box. Now, just tidy this up a little bit. If I divide through both sides by minus h bar squared on 2m, you can see that this gives me the second derivative with respect to the wave function or the eigenfunction. The constants disappear here, and these constants then reappear on the other side here. Now, h bar is a constant, m is a constant, and E will be at a particular energy, and we'll see that there'll be a number of energies, each characterized by an integer, the principal quantum number. So this combination for any particular state, stationary state or eigenstate, will just be a constant. So I'll write this equal to a constant. Now, for mathematical convenience, I choose to write this not as just a constant, but a constant squared. In fact, I'll choose to write this as k squared. And physically, k squared will be equal to 2me on h bar squared. But in fact, if I take the square root of this, this is none other than 2 pi on the wavelength, and this lambda here is the de Broglie wavelength. So that's what it means physically. If I was to choose not to take the square of this, I'd end up with the square roots of c throughout my solution. Now, I'll also rewrite this in a slightly tidier form. Physicists strive for elegance in writing equations, as indeed do mathematicians. So I'll rewrite this in identical form like this. And this is the equation I have to solve. Now, if you look at this, you'll see that you've met an equation of this form. In a classical context, this is mathematically identical to the equation of a harmonic oscillator. Of course, this is a quantum mechanical problem. So if you were to ask what is oscillating, it would be for any fixed point in space, the wave function will be oscillating in time. But we want to solve for the wave function as a function of x, or the so-called eigenfunction. So this is also known as an eigenfunction, or a proper function, or a characteristic function. So eigen is a German word, and we've fused the German word eigen with the English word function, the German word eigen with the English word value. So these are the proper values, the characteristic values, or the self values. When you act on the wave function or the eigenfunction with an operator, you return the wave function or the eigenfunction, and the thing that multiplies it is a real number. That's what you can measure. That's the observable. Now, we've seen in the workshop that a solution to this would be considered to be a superposition of two waves, one traveling to the right and one traveling to the left. And in fact, you'll get a superposition of these, which will give rise to standing waves. This is similar to the standing waves you get in a vibrating string, or this vibrating sound waves, or sound waves in a tube. And so a suggested solution would be the following. Now, this is not exactly how it's done in night. Night uses a slightly different but entirely equivalent approach to this. So here's my wave traveling to the right with certain amplitude, k vector or k wave number or wavelength, plus a wave traveling to the right. So that's the general solution. And indeed, you can substitute this solution into the equation here and show that indeed That's a solution to this differential equation. That's a solution to this differential equation. Because the Schrödinger equation is linear, the sum of the two are also a solution. So what we need to do is to impose boundary conditions on the general solution. It's by imposing these boundary conditions that I encode the physics of the problem. The physics of the problem is that this is a one-dimensional system. It's confined to an infinite potential well or a box. It has zero probability of being found on the walls or outside the box. And so I'll just impose the boundary condition that the wave function at x equals 0 must be 0. But if I put x equal to 0 here, I get e to the 0, which is 1. So this is the same as a. And if I put x equal to 0 here, I get e to the minus 0, which is also 1. So it's it's b. And since that must be equal to 0, this means that b is equal to minus a. Physically, what that means is if the wave comes in and sees the infinitely repulsive wall, the reflected wave must be inverted. So when I add them together, I get a node or zero probability of finding the particle there. I can write this suggestively as I pi a. And what this means is that there's a pi phase change upon reflection. Okay, so this means that the solution will look like this. Psi of x is equal to a, e to the I k x, but b is equal to minus a, so I'll just put a minus sign there. And because I'll take a outside the brackets here, I'll write this as e to the minus I k x. Now, I hope you'll recall from elementary mathematics that the cosine of some angle theta, or some argument theta, or x, or whatever you like to call it, is a half e to the I theta plus e to the minus I theta. I actually showed this. If you want, you can go back, look at your notes on complex numbers, and use the Euler form for this and this, and show that when you add them together, divide by 2, you get this. But in fact, I don't have a plus sign. I actually have a minus sign here. So if I subtract these two and divide by 2i, that's equivalent to sine of theta. So this is none other than 2i, so this expression here multiplied through by 2i, e to the I theta minus e to the minus I theta is 2i sine theta. So I can write this as 2ia sine of kx, and now I'll just call all of this combination of constants, including the complex or the imaginary number, I'll just call this another constant. And so we have the solution c sine kx. And that's the general solution. If you put x equal to 0, sine of 0 is 0. The interesting part is when you put x equals to L, what does the boundary conditions give you? And I'll return to exploring that in the next video.